Well, what if we have a reaction mixture that's not at equilibrium, but we've got both reactants and products, and what we'd like to know is this reaction going to go forwards or backwards when it's going towards equilibrium? So we have something called the reaction quotient that helps us figure that out. And that's abbreviated with a capital Q for quotient. So that can be in terms of concentration, moles per liter, or pressure in atmospheres. And the expression is the exact same thing as for the equilibrium constant. So the reaction quotient is equal to this same old mess for our little ABC equation here. The only difference is that when we calculate Q, we're doing that not at equilibrium. Because what we're trying to figure out is, okay, this is what we have right now, where are we going? When you get to equilibrium, Q is equal to K. It is the same thing. So Q is just calculating the equilibrium constant, but not at equilibrium, if that makes any sense. Yeah, any given time. So let's look at this graph, figure out what this is here. So we've got a reaction here. A is going to B. And the equilibrium constant expression would be the concentration of B over A. That means that the quotient concentration is the concentration of B divided by the concentration of A. So here, if we're starting out with only the reactant at 1 mole per liter and none of the product B, we see that as the reaction occurs, the concentration of A, no, we're looking at, I'm sorry, we are looking at the reaction quotient on the y-axis. So here, you would have B over A, so B is 0 and A is 1, and so the reaction quotient here is 0. Here, when we calculate it, let's write it out here. Q equals the concentration of B over the concentration of A. So at this point right here, then we've got 0.25 divided by 0.75, which I think is a third. No, it's not a third. 0.25 divided by 0.75. Yeah, it is. Oh, I was looking at this point. Okay, so here it's a third. As the reaction goes forward, the product concentration increases, the reaction concentration decreases, right? So as we go forward, the reaction quotient is going to get bigger and bigger and bigger. What would it be over here? What's 1 divided by 0? Undefined, right? You can't divide something by 0. This is going to go towards infinity, right? Because what if you had 1 mole per liter of products and 1 atom per liter of reactants, right? That'd be a ginormous number. So this is just going to keep increasing. The equilibrium constant, though, is constant. It's the same. Here, it's 1.45 because they told us it was 1.45. So no matter what our concentrations are, the equilibrium constant is always the same. At this point, right here, is where we have equilibrium, and that is where the concentrations plugged in give us the equilibrium constant. So Q is equal to K right there. So the usefulness of Q is we can compare Q to the known equilibrium constant and predict, is this reaction going to go forwards or backwards? So over here, when we calculate Q, we find out that Q is smaller than the equilibrium constant. So if Q is smaller, that means that the product concentrations are smaller than at equilibrium, the reactant concentrations are greater than at equilibrium. So if Q is less than K, that means the reaction is going to go forward. It's going to go to the right. Over here, because we could set this up so that our products are, the product is 0.75 and the reactant is 0.25. We stick those things together, a reaction is going to occur, and it's going to go in the reverse reaction until it gets to equilibrium. Because over here, we've got the product concentration being too high and the reactant concentration being too low to give the equilibrium constant. So if Q is greater than K, the reaction will go to the left. I don't think that explanation went very well. Ask me questions. Yes?
So I was wondering why the line keeps going up, if that's where equilibrium is, but it's to show you if you had like those concentrations, it would go
Yeah.
further.
So this line is just a line where we're saying, if this was the concentration, if this was the concentrations, if these were the concentrations, what would Q be? So that's what this blue line is. It's not necessarily that it's going to occur that way. It's just, if we start here, what's going to happen? If we start up there, what's going to happen? Any other questions? Yeah.
When you say it runs right, runs left, that just means like the reaction favors the product?
Yeah, so what does it mean running right or left? So this is an equilibrium. That equation is going in, or the reaction's going in both directions. And it's important to remember that at equilibrium, we still have the forward and the reverse reactions occurring. It's just that the concentrations don't change anymore. So what this says is going to the right means that the rate of reaction to the right is going to be larger. And so we're going to see an overall change where the reactant concentrations are going down, product concentrations are going up. Reaction running to the left means that predominantly we've got the reverse reaction happening, so we have more of the products reacting to form the reactants. And so we'll see that this concentration is going down and this concentration is going up. Did that answer your question? Yeah. Anybody else? So this is summarizing. We look at the reaction quotient relative to the equilibrium constant. So if the quotient is less than K, the reaction is going to go towards the right, to the products. If it's greater than K, the reaction is going to proceed to the left, towards the reactants. And when Q is equal to K, that means that the reaction is at equilibrium. The forward and reverse reactions then are happening at equal rates. We see no overall change in concentrations. Yeah.
So when it goes to that side has more higher concentration?
Yeah, so when the reaction is going to the right, towards the products, we see the product concentrations increasing. The reactants would be decreasing. And the opposite when it goes to the left. So at any particular temperature, there is only one value for K, the equilibrium constant. Q could be lots of different things. Q is just whatever state you are currently in. You can calculate Q, you compare it to K. Q is going to continuously change as the reaction progresses. It's going to change in a way that it will become closer and closer to K until it's equal to K, and then you're at equilibrium. Any questions? The Q is not supposed to be black, it's supposed to be green. So just, I fixed it yesterday, but apparently it didn't get saved. Doesn't matter, just let it go. Consider the reaction at its equilibrium constant. And notice here it says at some temperature. We really don't care what temperature, it's just important to say that we're doing all of this at the same temperature. So here we've got the reaction mixture contains these concentrations, and we're asked to calculate QC and predict which direction the reaction will proceed in. So we first have to write the equilibrium constant expression or the reaction quotient expression, same thing. So we don't have any solids or liquids, So we've got the concentration of products, and that coefficient is a 2, so we have an exponent of 2, and we're dividing by the reactants. The coefficient there is 1. So to calculate QC, I'm just going to plug in the current concentrations. So I'm told that NO2 is 0.0, that's not a 0, 0.255, and that's squared. This is 0. And N2O4 is 0.0331. I'm getting 0.0196 or 0.020. This one's written in scientific notation. I'm going to go ahead and write this in scientific notation. 2.0 times 10 to the minus 2. Anybody else get that number? Okay. So that's the first part, calculate QC. Now determine which direction. So is this larger or smaller than K? It's larger. And sometimes it's tricky with these negative exponents. If that messes you up, write it in decimal form, even if you have to count out a whole bunch of zeros. So what we have here is that QC is greater than K. Because our QC is 2.0 times 10 to the minus 2, and that's greater than the stated K, which is 5.85 times 10 to the minus 3. So the reaction will react in a way to make QC move towards the value of K. And it will do that until Q becomes K. I don't know about you, but I have a hard time with the whole, this is greater than, it goes this way, this is less than, it goes that way. I mean, it's just two things, and how do you put them together? So I prefer to just stop and think about it. So I've got QC as this thing, right? And it's too big. That means it's going to become smaller. Well, how does it become smaller? It becomes smaller if the numerator gets smaller and the denominator gets bigger, right? You okay with that? How does that happen for the reaction? How do I make the NO2 concentration less? The reaction has to go in the reverse direction, right? Shoot. Technical difficulties here. So the reaction proceeds to the left.